Alright, we're back with Chapter 29, Problem 3. And this question is rather interesting. It's addressing a model of the hydrogen atom known as the Bohr model, which treats electrons like orbitals, much like you'd see as a planet going around the sun. So the question is, ignoring the influence from the nucleus, if you had an electron whizzing around at a certain distance and you wanted to know what the B field magnitude was at the center of this electrical loop, what would that B field be? And so to solve, we've been given the radius and the velocity that the electron is orbiting from and traveling at. And so the first question we really need to know is let's start with this. I started it the other way when I did it myself, but let's go ahead and start with the Biot-Savart law, which states that B equals mu sub naught I over 4 pi, and then we have the segment, the small segment, times R unit vector divided by R squared. So we will go ahead and say if the electron is here, we want its ds, we want its small segment to point in the direction of the current. And of course, because the electron is whizzing that way, so is the current. So this is our ds vector. And then pointing inwards here towards the center is our r hat unit vector. And one thing you'll notice is that the ds and the r, because this is traveling at a constant velocity and it's not elliptical, it's purely circular, but the radius is always at a 90-degree angle with ds. We know that ds cross the r unit vector is going to equal to ds sine theta between ds and r. And that's theta is going to be 90, so that's going to actually simplify down to just ds, because sine of 90 is 1. And r is going to be a constant, because we're going around in a circle, we can pull r out. So we have b equals mu sub naught I over 4 pi r squared, and then the integral of ds, and the boundaries of ds, well, our segment starts here, it travels around the circle and ends up back here. So that sure looks like the length of the circumference. So we're going from 0 to 2 pi r. And the integral of ds is just s, evaluated at 2 pi r and 0, will just give us 2 pi r. So b will equal 2 pi r mu sub naught I divided by 4 pi r squared. The pi's cancel, that cancels to 2, that cancels to r. So what we've solved is that the B field at the center of the ring is going to equal mu sub naught I over 2 times the radius at the center of the circular path traced out by the electron. So now that we know the derivation for basically being at the center of a loop, current-carrying loop, now we just need to figure out some of the values here. So we know mu sub naught, we can look it up. We know 2 and we know r. R is given, so all we need to solve for is I. Well, I, in a system that's not changing velocity, so in other words, this system has no tangential acceleration. Of course, it has centripetal acceleration, but that won't matter because the current is going to equal to big delta Q over big delta T. And Q over T is for coulombs per time. Well, when the electron goes once around, we call that a period, and we indicate that with capital T. And let's just, for the sake of ease, leave the denominator as the period and the numerator as the charge of an electron, Q sub E. So in other words, coulombs per second is going to equal how long it takes for this to go around once. This is what the charge of it is divided by how long it takes for it to go around once. So how do we solve? Well, QE we know, it's 1.6 times 10 to the negative 19th coulombs. And period is going to be the more tricky one to solve. But it's not so bad. So we know that we're looking for the electron to go around once. the distance it takes to go around once is 2 pi r. And we know the speed it's traveling at. So we can divide the distance it travels by the velocity. And you'll notice that the distance is in meters, the velocity is in meters per second. And if we invert and multiply, the meters cancel, and we're left with the amount of time it takes to go around one full loop, which is the period. Alright, so now we know the period, therefore we know the current. So the current is Q sub E over, I'm going to invert and multiply it, times V over 2 pi r. That'll give us our current, so let's solve for the current and then plug it in to our derived value for the B field. Alright, so QE is 1.6 times 10 to the minus 19 coulombs times the velocity, which is given at 2.16 times 10 to the 6th meters per second, divided by 2 pi. The radius is 5.29 times 10 to the minus 11 meters. And so this is going to give us our current right here. So let's solve for it. 1.6 times 2.16 divided by 2 divided by pi divided by 5.29 gives us 0.104 roughly times 10 to the negative 19 plus 6 plus 11. That's to the minus 2. And the units there is in amps. Now we can go ahead and plug this value into this equation. And B equals mu sub naught, the permeability of free space is 1.26 times 10 to the minus 6th times the current, which we solve for at 0.104 times 10 to the minus 2, divided by 2 times the given radius of 5.29 times 10 to the minus 11. And let's figure out what we get. 1.26 times 0.104 divide 2 divide 5.29 gives us 0.012 times 10 to the negative 6 minus 2 plus 11 to the 3. We move the decimal place 3 to the right and we end up with the B field equaling 12 Tesla. And that is the answer for this problem. And that's quite a large number. 12 Tesla is unlike any magnet you've ever seen in your life, I can guarantee it. So that's really interesting. It's way higher than I expected it would be. But I guess it takes a lot of energy to keep the electron at that speed from flying off. So hopefully this was helpful, and I'll see you next video.